Hi everyone, so in this video I want to introduce the idea of a random variable. In particular, we'll be working with a discrete random variable and talk about how we can calculate probabilities of random variables. And so to motivate these concepts, let's consider the following example. So suppose we know that 1% of all lithium batteries manufactured by a company are defective. The company sends a shipment of 10 batteries to a client. How likely is it that none of the batteries in that shipment are defective? And so we're going to make an assumption in this example and in what follows that each time we pick a battery, the likelihood that it's defective is 1%. So every single time we pick a battery, it's a 1% chance of being defective. Each battery that we pick is independent of the next battery that we pick. So let's first consider what the sample space of this experiment would look like. So here we're picking 10 random batteries. And so for example, one possible outcome would be none of the batteries are defective. And so here a G denotes that we picked a good battery. So we have the first battery is good, second battery is good, all 10 batteries that we pick are good. So that's one possible outcome from this experiment, that we pick 10 good batteries. Of course, all sorts of other things are possible. It's very possible that we send a shipment that has one defective battery. And there are more than one outcome that would lead to that. So for example, we are going to consider this outcome, which is the first battery is defective, the last 9 are good, as a different outcome from the first battery being good, the second one being defective, and all of the rest being good. So we have a whole bunch of ways, in fact, 10 of them, 10 different outcomes that would have one defective battery in it. And we can list all sorts of different outcomes. Here would be examples of 2 defective out of the 10, and we can go on and have all possible different outcomes where we have 3 defective batteries out of the 10. So there's a lot of possibilities here. And rather than list out all of these outcomes, there's a whole lot of them, let's consider how many different outcomes are in this sample space. So in other words, how many different possibilities are there if we send 10 different batteries? And so here's a counting argument. And if you think about it, for each battery that we pick, we have 2 choices, either a D or a G. So I have 2 choices in the first position, 2 choices in the second position, and so on. And altogether, since we have 10 batteries that we are sending, this is going to give us 2 to the 10th, which is 1,024 possible outcomes. So this is a very, very large sample space. So we would like to do some analysis without actually having to list all of these outcomes. And so one thing that we might want to consider if we're thinking about, well, how likely is it that we get a shipment of no defective batteries? So we get 10 Gs. What you don't want to do is a simple counting argument that we've seen in the past. So for example, I wouldn't want to say, well, there's 1,024 possible outcomes. Only one of them results in 0 defective batteries. So there's a 1 out of 1,024 chance. And the reason why this is not correct mathematics in this case is because in this example, not all of the outcomes are equally likely. So it's not equally likely to get 10 good batteries as it would be to get 9 good batteries and 1 defective one. So we need to approach how we calculate probabilities in this example a little bit more carefully. So for example, if 99% of the batteries are good, you'd be much more likely to get 10 good batteries than you would to get 10 bad batteries, but we'll unpack the mathematics on that in a second. And so considering the battery example from the previous slide, we might ask questions like, what is the average amount of good batteries that are going to be sent in the package? What's the standard deviation for the number of good batteries that are sent in the package? So we might want to do some more mathematical analysis. So in order to do that, how can we attach some number to each of these outcomes in a meaningful way? And so to do that, we can introduce what's called a random variable. So a random variable, by definition, is a mapping from the sample space into the real numbers. So we're going to assign each individual outcome in the sample space a value. And so let's take a look at an example. Let's come back to this battery example to see what a random variable might look like in that example. So in this case, our sample space omega is all of the 2 to the 10th possible outcomes. So that was like the 1,024 different outcomes. And so for each of these outcomes, we're going to count up how many good batteries appeared in that shipment out of those 10 batteries. And so that's going to give us a way of mapping each of these strings of D's and G's into a number. So some examples of what this random variable would look like. So here are some different outcomes that we've talked about. And so for this one over here, if we have 10 good batteries, the random variable is going to map this outcome to how many G's appeared in that string, which is 10. This outcome would be mapped to 9 because it has 9 G's in it. This is a different outcome that has the same map value 9. And over here would be an example of we had 5 D's and 5 G's. So this outcome gets mapped to 5. So a random variable is a function. It's a map from the sample space into the real numbers. So a couple of things to note here, and that is this is not a one-to-one map. It's possible that we have two different outcomes that get mapped to the same value. So we've seen that there are many different ways that we could have an outcome that has 9 good batteries. And secondly, in this example, we see that since we're counting how many good batteries we have, the range is 0, 1, 2, 3, 4, all the way up to 10. So in this case, when we're counting, our range is a discrete set of values. So therefore, we would call this a discrete random variable. And what's the point of all of this? By attaching values to each of these outcomes, it's going to allow us to do more statistical analysis. How many good batteries should we expect in each shipment? What's a reasonable spread of values that we might expect for the number of good batteries, and so on. Okay, so far we've talked about what a discrete random variable is in the case of the batteries that are being shipped. And what we would like to do is attach some probabilities now, like how likely is it that we get no defective batteries, one defective battery, and so on. And so to do that, we can define what's called a probability function. In the case of a discrete random variable, we might call this a probability mass function, which often gets abbreviated with PMF. And so we can describe this probability mass function for random variable x. Sometimes you might see it written using more functional notation. More likely, you see it using this probability notation. We'll use both. And so to motivate this idea of a probability distribution, let's consider the same motivating example where we have a shipment of 10 lithium batteries where each lithium battery has a 1% chance of being defective. And the original question was, well, what is the probability that none of the batteries are defective? And so we don't want to handle this by a counting argument. How many outcomes are there? How many outcomes satisfy this event? Because again, each of these outcomes is not equally likely to occur. So let's consider this from another point of view. So there is only one outcome in this example with x equals 10, where all 10 are good. And that would be the outcome where we have a string of 10 G's. And so to calculate this probability, since there's only one outcome, we just need to calculate, well, how likely is it that we would get 10 G's in a row? And what's nice is because each battery that we pick is an independent event from the previous battery that we pick, we can use the fact that when we are working with independent events, we can just take the product of each of these probabilities. So I can calculate what's the probability that the first one is good. Well, that's a 99% chance, times the probability that the second one is good, and so on. So we can't do this in general, but because we're working with independent events, we can break up this into individual products. So that means we know that the probability of getting a good battery on any one selection is 99%. So the probability of getting all 10 good batteries would be 0.99 to the 10th power, which comes out to about 0.9044. So in other words, there's about a 90% chance that you get a shipment where all 10 batteries are good. None of them are defective. And so as far as the notation goes, you can see that we might write this that P of X equals 10 is 0.9044. You also might see it written that the probability function of random variable X, when we evaluate it at X equals 10, gives us this. So they're both expressing the same fact, just using slightly different notation. And let's practice just a couple of more similar calculations with the battery example. So now let's consider we're sending 10 batteries. What is the probability that all 10 of them are defective? So the first one is defective, the second one, and so on. Well, that would be really unlikely to occur. And we can see that, in fact, we only have, again, one outcome where X is 0, where we have 0 Gs. And that would be the one where we have all 10 Ds. And using independent of events again, we would say, well, the probability of getting one defective battery on the first one is 0.01, and then it's 0.01 again. So we have 0.01 to the 10th power, which gives us an extremely small number. Basically, it's essentially a 0% chance that we would get all 10 defective batteries. If we wanted to calculate, well, what's the probability of getting exactly one defective battery? Well, this is a little bit more complicated than the previous two because there are 10 different outcomes in our sample space that have 9 Gs in it, right? We could have one, the first D, and then 9 Gs after that. We could have a good battery, defective, then 8 good batteries, and so on. So there are 10 different ways the D can be in the first slot, the second slot, the third slot, all the way out here at the 10th slot. So we have 10 different outcomes that have X equals 9. And all 10 of these outcomes have the same likelihood of occurring. So let's see how we can calculate the likelihood of any one of these from happening. So for example, this first one is defective, the next 9 are good. Again, we've got independent events, so we can calculate the probability of the D times the probability of the G 9 times over. So that looks like 0.01 times 0.99 to the 9th. So that gives us approximately this much is the probability. 0.009135 is the probability of just this one outcome of occurring. And if we change the position where the D is, it's not going to change the probability of that event occurring. So each one of these 10 different events where we put 10 different outcomes, so depending on where we put the D in this sequence, they're all going to have the same probability. So altogether, if we want to calculate the probability that X is equal to 9, that we get exactly 9 good batteries, I could take this probability over here and then add it to this probability over here. And actually, we're adding all of these probabilities. And since all of these probabilities all are the same, it's equivalent to saying 10 times the probability of any one of those outcomes occurring. And so for this, we can see that the probability of getting exactly 9 good batteries is about 9%. So it's 0.09135. And you might be thinking this seemed kind of complicated. And so we'll break this down more carefully in class. And in fact, we'll find that there's a formula that we can generalize this process to calculate probabilities of experiments that fall into this category, what's called a binomial experiment. So let's just kind of summarize things on the last slide. And so when we're working with a probability distribution for a random variable, in this case, a discrete random variable, it's a function. So just like in algebra, calculus, we can represent these functions with a table, with a formula, sometimes with a graph. So for the example with the 10 lithium batteries being shipped, we could summarize all of the possible outcomes. So there are 11 different possible values for X here. You could get no good batteries all the way up to 10 good batteries. And this is just telling us what is the probability of getting no good batteries, 1 good battery, all the way up to 10. So these were the probabilities that we calculated, some of them on the previous slides. To make this look a little bit more formal, you might want to take this table and represent it as a function. In this case, we don't have a formula, but we could write this as a piecewise function by saying, given each of these inputs, like x equals 0, here's the output. When x is 1, this is the probability of getting 1 good battery, and so on. And when you have a whole lot of different outcomes like this, and a whole bunch of different values for the random variable, it might be nice to represent this visually using a graph. So here's a probability mass function. So what's going on is over here is the probability of getting all 10 good batteries. So this point over here, well, this has a corresponding y value of 0.9043. So that comes from this output that we had over here. And this point over here corresponds to this output over here. And then for all of these values, 0, 1, 2, 3, you can see that the corresponding probability of getting x equals 0 or x equals 1 is essentially 0. So that's why all of these points over here are very hard to read because they're all basically 0. It isn't until we get about 9 or 10 good batteries that the odds are pretty high that that would happen, and we can actually distinguish those points on the graph. Here was the one for 9, and here was the point for 10. So we'll take a look at some more examples in class and come up with some ways of doing these calculations a little bit more efficiently.